Next, we have a talk about the paper GitSchemas, a data set for automating relational data preparation tasks. So Till will present this paper. Till, the floor is yours whenever you're ready.
Hi, thank you, Nantia, for the introduction. Hope you can see my slides, and I will start the talk. So my name is Till Döhmen. I'm a research assistant at Fraunhofer FIT, and the work on GitSchemas was done in collaboration with the University of Amsterdam, among others with Madelon Hulsebos, where Paul Groth just talked about project Git tables. But in this work, we focus on schemas. So that's why it's called GitSchemas, and it's a data set for automating relational data preparation tasks. The idea came when we were working on AutoML in data lakes. So there the problem is you have to basically identify relevant data sets in the data lake, find relations between them, so you can join, aggregate, so basically prepare them to features and until they can be fed into machine learning training. So, and in this finding relations part, we encountered the foreign key detection problem. So we have multiple tables and we have to find a way basically to combine them. We don't have schema information necessarily, so we have to identify foreign keys in those different tables. And there are, of course, existing methods like value-based methods, but they, especially for ID columns, they have a limited reliability. So because we can get false positives quite easily when we look at ID columns, which might be just an increasing ID, we can have very high value overlaps, so high set intersections, which are the primary signal for this value-based method. And you know, why here in this example on the right side, the actual correct join has a lower intersection. Then another category of methods are schema-based methods. So there we have, often those methods look at string similarities between table names or column names to identify which could be potential foreign key joins. And also here, these methods are not always correct. And because on the left side we have both columns are called user ID, but this is not necessarily the join which makes most sense in that context. So we thought, okay, can't we improve these schema-based and value-based methods with an additional signal, which comes from a large repository of commonly used foreign key relationships? Because we as humans, when we look at this at these schemaless data, we might already have an intuition because we know we have modeled database schemas before. We've seen database schemas before, so we have an additional kind of background knowledge. And the idea was to provide this as well to the foreign key detection methods. And then in the easiest case, we would just have a whitelist or checklist, which we could look up. Is this potential match something we have seen before in other schemas? And then, of course, you could also, once having this resource of common foreign key relations, I could also think of training an NLP-based method, or also maybe a graph-based method, as was presented in the first talk today. I think this is also a very interesting direction for this kind of data. So we could have a more generalizable prediction model for foreign keys. So we looked around basically for data sets, and the largest data set which actually contains schemas we could find was the CTO Prague Relational Learning Repository, which is a really great resource, by the way, for machine learning problems on relational data. But it has by far not the extent we were looking for. And then on the other hand, there are, of course, these corpora like web tables or Git tables, which contain millions of tables. But there we are simply lacking the schema information. We are looking for. So like foreign keys, primary keys, data types, and so on. But still inspired basically by the work of Git tables by Madelon, where it is about also getting realistic data, representing real-world enterprise-like data. We also turned to GitHub, and we created GitSchemas. And this is a data set consisting of real-world database schemas, not the data, only the schemas, and it so far covers approximately 50,000 databases, 300,000 tables, and 2 million columns. And beyond foreign key detection, we think it opens up possibilities for other interesting use cases as well, because we have primary key information from all these different schemas. We know how primary key columns are called in all those different schemas, and we could maybe learn also an NLP-based model or develop other kinds of heuristics which predict which columns are ID columns in, for example, CSV files. Or we can predict data types as well for schemaless data. Also, maybe for data where we don't know the data types in terms of, is it a string column or is it an integer or float column. We have this information from the schema, and we might be able to learn it from there. Or for parsing CSV files, there's a particular problem where you don't know whether the first row in a CSV is a header row or not. So we could look, we have 2 million column names, right? So we could just look at our corpora and see, oh, how many matches do we have in this first row of the CSV? And this could give a really, really good signal of whether the first row is a header or not, depending on how many matches we find. So, and that's why we wanted to present it here as well. We think there might be much more use cases which we don't have on our radar yet. Yeah, so let's turn to the collection process, which is quite straightforward in a sense. So we use the GitHub API to crawl SQL files, or to search SQL files, particularly containing create table and foreign key statements. So to filter them to schemas which are to SQL files which are schema defining. So, and we end up with 700 out of 700K out of 7.8 million SQL files which are in the GitHub index. And subsequently we download them, deduplicate them, and then extract the schema information from the SQL file in a structured way. And we end up with 50,000 of these schemas. So why do we only end up with 50,000 schemas? We took the following approach. We take the SQL files and then use a standard SQL parser. And we tried out different implementations of SQL parsers, which were readily available in Python. And pglas, which is basically the standard implementation of the PostgreSQL parser, it had the highest success rate on the files. These files, of course, are written for different databases. So it was a challenge to find a parser which just works out of the box for a lot of different files, and we had the highest success with pglas. But of course, there's still a lot of room for improvement. But nevertheless, with this library, we extracted the abstract syntax tree, and from there we can then extract the structured schema information quite easily. So we get table names, column types, primary keys, foreign keys, also primary composite foreign keys. And we collect the usual metadata, which also includes licenses. So let's have a look into the data. When we look at the data set, we see the most common table names are users, employees, departments. So quite the kind of tables we would expect to be common in this for enterprise enterprises. And at the same time, there's also a breadth to the data set. So we can see when we just sample a table starting with product, see a lot of small, a lot of different tables relating to products basically. And also random sample shows it covers a lot of different domains, like from reviews to quite technical things like sys maps. And the same also holds for the column names then. So the most common column name is what we would expect to be ID, name, description, and so on. But also we have very a lot of different column names referring to users, all kinds of different column names we could think about. And then the random sample again shows the breadth also of domains. And for foreign keys, we have 200, or for primary and foreign keys, 250,000 primary keys. The most common being ID, what we could expect, and again 140,000 foreign keys, 30,000 unique names, and a low amount of composite foreign keys. They are not that common in this corpus, it seems. So, and the foreign keys, or before we go there, first we have to talk about the licenses. So because only a subset of the data actually permits redistribution of the licenses, we will provide basically the script for reproducing the full corpus. Unfortunately, we cannot at this point. We're not very confident about releasing the full data set. It might be possible, but we're not sure at this point. So we would definitely these permissively licensed schemas, of the schemas which were extracted from permissively licensed SQL files, they are available as direct download also on GitHub. The others have to be reproduced with a script. Yeah, but let's turn to exemplary use case for this corpus, which goes back to the initial introduction. So we want to improve an end-to-end machine learning pipeline using GitSchemas, and we want to do data augmentation, which means we have this core table users, which contains our target reputations. So it's like an online forum, and there are users and they have a reputation, and we want to build a machine learning model predicting those. And there might be other tables like this table here, badges, like users get badges for certain achievements. And there's a relation between them, right? This user ID here suggests we can join it. We can join the badges with the users table, and then we have additional features which will hopefully increase the accuracy of our machine learning model. So that's the context. And now we just use the conventional foreign key detection method. It's called Cupid. It's a schema-based method, and it ranks the ID columns. So if we go back here, the first two columns, it suggests them with the highest likelihood to be the correct joins. And but they are actually in fact not the correct joins. So when we just run the AutoML pipeline and assume the highest ranked join candidate is the right one, it will it will even deteriorate the model quality, because we will lose data by the join. We will end up with wrong features basically, because the join doesn't make in a semantic way doesn't make sense. So this is something we definitely want to avoid when we say we want to end-to-end automate this process. And then the idea is to use GitSchemas and basically to just look up, do we have any relations between the users table and the badges table in our corpus? And we find actually two matches. And these are not coming from the same data set. We check that. So it's not that we have that our example use case somehow leaked into the GitHub schemas we called. These are different schemas, let's say. And so when we use this, the results we found, and basically re-rank our candidates just based on string distance here to the lookup results, then we end up with the correct join being ranked highest, and then our data augmentation works correctly, and we can increase the model's accuracy. Yeah, and that's the use case. It's of course a very limited use case or experiment, just to give a first sense of how this data set could be used in a simple way. And in general, we have high expectations about Git schemas being useful for the community, and we really want to explore other use cases which go beyond what we showed now. And it is, to our knowledge, the largest data set of that kind. And we want to make it bigger in the future. So we want to improve the parsing process so we can also share a bigger corpus without having the license concerns. So we can just publish the MIT Apache license files and have a higher recovery rate of them by using parsers like Apache Catsite, for example. And we hope to inspire new use cases and applications in general. Yeah, and that's basically it. And thank you very much for the attention, and feel free to reach out if you have any questions. Feel free to go to the GitHub repository and take a look at the data yourself. Thank you.
Thank you very much, Till, for the very nice presentation. Are there any questions? So yeah, I can start with one first. First, just a comment. It was quite surprising to me that that it's so hard to actually parse SQL create statements, because SQL is highly standardized. So I was expecting that the parsers would be better, but yeah, apparently there are challenges there. So a question that I have is, would it be an option, because as you said, the tables that you found on GitHub are more enterprise data, so it's employees or products or these types of data. So would it maybe be an option to look into ML repositories, and although data there are more CSV files, but to like get a schema for these data from the CSV headers probably, and also augment what you already have with this type of data?
So, okay, thank you for the question. First to the comment with the CSV, with the SQL parsers, it's really something which surprised us as well. And it's probably, I guess it's a problem which usually doesn't come up, because usually when you write SQL, the target platform is known. But now this kind of turns it around, and we have SQL for like all kinds of databases, and there are also often subtle differences, like how basically column names are quoted or table names are quoted. MySQL uses this tick, this accent symbol. Other database use a single quote. Others might use double quote, and so on. So and these subtle differences make it hard. Yeah, so to the other question, I should have mentioned on the slide where I said web tables, Git tables, also should have mentioned something like Kaggle. For sure, we looked into that as well. Actually, I have a quite big corpus of Kaggle data sets. And that's how we originally, or how I originally started out to see, okay, maybe I can use Kaggle data to get some realistic data sets to approach this AutoML and data lakes problem, basically. But there you get maybe 100 data sets. And it's quite similar to the relational data repository, which there's even an overlap with Kaggle from there. So it's in the realms of 100 databases, maybe. And I mean, the benefit is you have data, right? And that's I think something we want to look into as well. Now that there is GitSchemas and GitTables, you could think of, okay, we have this enterprise-like single tables and we have enterprise-like schemas. So maybe we can just combine them to have a really big corpus of realistic data sets which have data as well as schemas.
Mm-hmm. Yeah. I see. Thank you. Thanks a lot for your answer. We have like 1 minute for a brief question, if there is any. All right, then thank you, Till, again.